early January. Yeah.
Yeah. Mm-hmm. Yeah. Now I was at UCI. We had quarters, so we will start later, but we will finish in like mid-June.
Okay.
So
Early January.
yeah. All right. So I started the stream. I will also start recording, and I just want to thank everyone for joining, and in particular, thanks to Neil who's taking the time to give this exciting talk. We're all looking forward to it. So just a very quick introduction for anybody who might not know who Neil is. So he's an assistant professor at Duke University. He got his PhD from UC Berkeley, and is overall working sort of on topics at the intersection of security, privacy, and machine learning, and has a number of accolades, including NSF Career Award, ARO Young Investigator Program Award, Rising Star Award, IBM Faculty Award, Facebook Research Award. So a lot of awards, including a best paper or honorable mentions. So I'm really happy to introduce Neil. And Neil, we typically have 1 hour. Obviously, it'd be great if you could leave some time for questions. Up to you if you want to take questions. I might need to sort of hide myself as I walk to pick up my daughter from school, but I will be listening in. And maybe if I can't sort of unmute myself, I'll ask somebody else to sort of moderate the Q&A, but I will be listening. So
yeah,
thank you so much. Thank you. Take it away.
Yeah, thanks for the introduction and inviting me to give this talk, Emiliano. Hello, everyone. As Emiliano introduced, I am Liu Gong from Duke University. Today, I will share with you our research on secure self-supervised learning. By the way, you guys can ask me questions at any point of time during this talk. Okay. So, as you know, supervised learning is a very popular conventional machine learning paradigm. Suppose we're given a learning task, such as traffic sign recognition. Supervised learning first requires manually labeling a large amount of traffic signs, and then trains a classifier. Given another learning task, such as digit recognition, supervised learning requires first manually a large amount of digits, and then trains a classifier. In supervised learning, this process of manually labeling a large amount of labeled training data and the training classifier is repeated for each individual task. So the key challenge of supervised learning is that it requires a large amount of labeled training data for every task. Self-supervised learning aims to address this key challenge. Specifically, given a large amount of unlabeled data, self-supervised learning aims to pre-train a neural network, which is known as encoder. The pre-trained encoder is then used as a general purpose feature extractor to build classifiers for different tasks. Given a pre-trained encoder, building a classifier for a task only requires a small amount of, or even no labeled training data. Self-supervised learning has made substantial progress in the past several years, and many encoders have been pre-trained by industry. For instance, CNIP, BERT, GPT, and so on. While there are already many studies on improving the accuracy of self-supervised learning, its security aspect is much less explored. So in this talk, we will discuss the security of self-supervised learning. In particular, we will focus on the security of pre-trained encoders. Moreover, we will focus on pre-trained encoders in the computer vision domain. By analogy to a computer system, a pre-trained encoder is like an operating system of the AI ecosystem. So studying the security of pre-trained encoder is like starting operating system level security of AI. This is a roadmap of this talk. In part 1, we will discuss our backdoor attack to pre-trained encoders. And in part 2, we will discuss data auditing for pre-trained encoders. Let's look at part 1 first. Before introducing our backdoor attack, I'd like to describe a little bit more background on self-supervised learning. Suppose we're given some unlabeled data, which could be images or image-text pairs. These unlabeled data are often collected from the public internet, such as social media sites, Google search, and so on. Given these unlabeled data, self-supervised learning aims to pre-train an encoder, and the pre-trained encoder is then used as a feature extractor to build classifiers for different tasks. In self-supervised learning, these tasks are often called downstream tasks, and these classifiers are often called downstream classifiers. Next, I will describe a little bit more details about how to pre-train an encoder from unlabeled data and how to build a downstream classifier based on a pre-trained encoder. Data augmentation is a key component of pre-training an encoder. Suppose we are given an image. Data augmentation aims to create random augmented views of this image. For instance, we can crop a random region of the image and then resize it to have the same size. We can also flip the image, rotate the image, or use many other operations to create random augmented views of the image. Next, let's use same CLR as an example to illustrate encoder pre-training. Suppose we are given an image. We first use data augmentation to create 2 random augmented views. We have an encoder. We use the encoder to produce a feature vector for each augmented view. We are also given another image. We also create 2 random augmented views using data augmentation and use the encoder to produce a feature vector for each of them. An encoder is basically pre-trained in a way such that it produces similar feature vectors for 2 random augmented views of the same image. But these similar feature vectors for 2 random augmented views created from different images. Suppose we're given a set of training inputs of a downstream task and a pre-trained encoder. We first use the pre-trained encoder to produce a feature vector for each training input. These feature vectors and the corresponding labels are then used to build a downstream classifier. For instance, following the standard supervised learning paradigm. Given a testing input, we use a pre-trained encoder to produce a feature vector for it, and then use a downstream classifier to predict its label. In a backdoor attack to self-supervised learning, an attacker aims to achieve 2 goals. The first goal is a utility goal, which means that the classification of a clean test input should not be affected by the backdoor attack. For instance, in our example, this clean stop sign image should still be correctly predicted as a stop sign. The second goal is the effectiveness goal, which means that once we embed a backdoor trigger, for instance, a white square in our example, into any testing input, the classifier predicts an attacker-chosen label. For instance, speed limit in our example. This attacker-chosen label is often called target label. Existing backdoor attacks, when applied to self-supervised learning, aim to compromise the downstream classifiers to achieve these 2 goals. However, these backdoor attacks are not applicable when the process of building a downstream classifier maintains integrity. Our backdoor attack aims to compromise the encoder to achieve the two goals. Specifically, given a clean encoder, our backdoor attack, called bad encoder, transforms it into a backdoor encoder. When the downstream classifiers are built based on our backdoor encoder, they inherit the backdoor behavior simultaneously. For simplicity, let's denote the clean encoder as F and the backdoor encoder as F prime. In our attack, we consider the following threat model. Suppose an attacker aims to attack one target downstream task. For instance, traffic sign recognition. The attacker picks one target label, for instance, speed limit, and one backdoor trigger, for instance, a white square in the center of an image. Our attack can also attack multiple target downstream tasks and multiple target labels. But for simplicity, let's focus on just one target downstream task and one target label in this talk. The details of attacking multiple target downstream tasks and multiple target labels can be found in our paper. The attacker aims to achieve the effectiveness goal and the utility goal. In terms of the attacker's background knowledge, we assume the attacker has access to some unlabeled images, which we call attack dataset. The attacker also has an image with a target label. For instance, when the target label is speed limit, this image is a speed limit sign. We call this image reference image. An attacker can collect the attack dataset and the reference image from different sources, for instance, the public internet. The key idea of our backdoor attack is to formulate it as an optimization problem. Specifically, we propose an effectiveness loss to quantify the effectiveness goal, and an utility loss to quantify the utility goal. Then, given a clean encoder, we generate a backdoor encoder via minimizing a weighted sum of these two losses. Next, I will describe more details about how to quantify the effectiveness goal and how to quantify the utility goal. The effectiveness goal means that any image with the backdoor trigger should be predicted as a target label. Specifically, we first use the backdoor encoder F prime to produce a feature vector for any image with a backdoor trigger. Here, F prime X is a feature vector for an image X produced by the backdoor encoder F prime. Then the downstream classifier should predict this feature vector as a target label, which is speed limit in our example. We propose two conditions, satisfying which can achieve the effectiveness goal. The first condition is that the backdoor encoder F prime should produce similar feature vectors for any image with a backdoor trigger and the reference image. The second condition is that the backdoor encoder F prime and the clean encoder F should produce similar feature vectors for the reference image. So the feature vector of the reference image produced by the backdoor encoder F prime is still correctly classified as a target label by the downstream classifier. We can achieve the effectiveness goal by satisfying the two conditions. So quantifying the effectiveness goal now becomes quantifying the two conditions. We use the following loss term error 0 to quantify condition 1. Here, DA is the attack dataset. F prime is the backdoor encoder. X plus E means embedding the backdoor trigger E into an image X. XR is the reference image. S is the similarity metric used to measure the similarity between two feature vectors. In our experiment, we use cosine similarity. This term is the attack dataset size and is used to normalize the similarity scores. Intuitively, a smaller L0 indicates that condition 1 is better satisfied. We use the following loss term L1 to quantify condition 2. Again, F prime is the backdoor encoder, F is a clean encoder, XR is a reference image, and S is a cosine similarity between two feature vectors. Intuitively, a smaller L1 indicates that condition 2 is better satisfied. Finally, we quantify the effectivity score using a weighted sum of the two loss terms. Here, lambda 1 is a hyperparameter used to balance between the two loss terms. The utility goal means the classification of any image without the backdoor trigger should not be affected by the backdoor attack. To achieve this goal, we want the backdoor encoder F prime and the clean encoder F to produce similar feature vectors for any image X without the backdoor trigger. Formally, we use the following loss term L2 to quantify the utility goal. Again, DA is the attack data set. S is a cosine similarity between the two feature vectors of an image X produced by the backdoor encoder F prime and the clean encoder F. Intuitively, a smaller L2 indicates that the utility goal is better satisfied. Finally, we have the following total loss L, where L0 and L1 quantify the effectivity goal, while L2 quantifies the utility goal. Lambda 1 and lambda 2 are two hyperparameters used to balance between the three loss terms. Given a clean encoder F, we generate a backdoor encoder F prime while minimizing the total loss L. Moreover, we minimize the total loss L using stochastic gradient descent. In our experiment, we pre-train an encoder using SimCRR and the Cepha-10 dataset. In this talk, we also evaluated our attack on encoders pre-trained on multiple other datasets, and the result can be found in our paper. When building downstream classifiers, we consider 3 downstream tasks, and we adopt a fully collected neural network as a downstream classifiers architecture. In our attack, we assume the attack dataset is the pre-training dataset. The target label is different for different target downstream tasks, and the details can be found in our paper. The reference images were collected from the public internet. The hyperparameters lambda 1 and lambda 2 are set to be 1. We also evaluated our attack under many other attack settings, and the details can be found in our paper. Recall that our attack aims to achieve the effectivity goal and the utility goal. In order to evaluate whether our attack achieves the effectivity goal, we use attack success rate as an evaluation metric. Specifically, suppose we're given some clean testing input. We embed the backdoor trigger into each of them. Then we use a backdoor encoder F prime to produce their feature vectors. And finally, we use a downstream classifier built upon F prime to predict their labels. We define attack success rate as a fraction of the testing input embedded with the backdoor trigger that are classified as a target label, which is speed limit in our example. This table shows the attack success rate of our attack for the 3 target downstream tasks. As we can see, our attack achieves the effectiveness goal because the attack success rate is close to 100%. We use clean accuracy and backdoor accuracy to evaluate whether our attack achieves the utility goal. Again, given some clean testing input, we first use a clean encoder F to produce their feature vectors, and then use a downstream classifier built upon F to predict their labels. Clean accuracy is a fraction of the testing input that are classified correctly in this way. We also use the backdoor encoder F prime to produce the feature vectors of the test input, and then use the downstream classifier built upon F prime to predict their labels. We define backdoor accuracy as a fraction of testing input that are classified correctly in this way. Our attack achieves the utility goal if the backdoor accuracy is similar to or even higher than the clean accuracy. This table shows the clean accuracy and the backdoor accuracy of our attack for the 3 target downstream tasks. As we can see from this table, our attack achieves the utility goal because the backdoor accuracy is similar to or even higher than the clean accuracy. We also evaluated our attack on real-world pre-trained encoders. In this talk, I will show you some results on OpenAI's pre-trained encoder called CLIP, which was pre-trained on 400 million image-text pairs collected from the public internet. Our results on other real-world pre-trained encoders can be found in our paper. We assume the attack dataset is the imagelet dataset, since the CLIP's pre-training dataset is not publicly disclosed. This table shows the results of our attack for CLIP. First, our attack achieves the effectiveness goal because the attack success rate is close to 100%. Second, our attack achieves the utility goal because the backdoor accuracy is similar to the clean accuracy. We also found that existing backdoor defenses designed for supervised learning are insufficient to defend against our backdoor attack. Specifically, we evaluated both empirical defenses and provable defense. For empirical defenses, we evaluated neural cleans and MNTD. For provable defense, we evaluated PatchGuard. We found that neural cleans cannot detect our backdoor encoder. The detection accuracy of MNTD is close to random guessing, and PatchGuard has insufficient provable robustness guarantees against our backdoor attack. To summarize a little bit, we showed that pre-trained encoders in self-supervised learning are vulnerable to backdoor attack. Insecure pre-trained encoders lead to a single point of failure of the AI ecosystem. And existing backdoor defenses are insufficient to defend against our backdoor attack. So that's part 1 of this talk. And let's see, do we have any questions about part 1? Yeah, Ziqing, go ahead.
Hello, thanks for your presentation. My question is that how do you treat the classifier based on your encoder? Maybe both the backdoor encoder and the plain encoder. Okay, good question. So how to train the classifier? Let me go back to the slide in the background part. Okay. Yeah, here, this is one more slide. Yeah, this is how we train a downstream classifier. Is this what you mean? Oh, yes, because for the labels, and do you use the clean label, or how do you choose the? Yeah. Okay, good question. The labels are clean for the downstream task. For the downstream classifier, the training data set is clean. We don't manipulate, we don't poison the training input nor the labels of the downstream classifier. Yeah, we only compromise the pre-training part. Oh, okay. And also, do you consider the situation that sometimes when people use the downstream classifier, they will also fine tuning the encoder?
Oh, that's a very good question. That's a very good question. And so first of all, in our work, we use linear probing to train the downstream classifier. And so what you are saying is basically fine tuning, right? When you build the downstream classifier, instead of just training the downstream classifier's model parameters, you train both the pre-trained encoder and the downstream classifier. Okay. A short answer is that we haven't tried this. Okay, but I think it's very interesting to check to verify whether our backdoor tag still works if the downstream customer uses fine tuning instead of linear probing to train the downstream classifier. And actually, even more interesting follow-up question is, if our backdoor tag does not work in this case, how to improve, right? How to improve the backdoor tag such that it survives from fine tuning? Yeah, I think that's a very good question. Thanks for the question. Okay, I think there are other questions. Go ahead.
Yes, so next question will come from Yiting.
Okay, go ahead.
Hello, Professor Neil Gong. Thank you so much for your wonderful speech. I am Yiting from CISPA. I actually have a question about the formulation of the loss function, where you formalize it into two different goals: effectiveness goal and utility goal. And I think when you formalize these two goals, we all use the fact that we think for any given image, we think the features from the BATnet and from clean encoder should be as similar as possible. So my question is, isn't this some overlaps in some way in these two goals?
I see your point. I see your point, because here, I guess, let me repeat your question first. So I'm guessing what you mean here, because here, look at the utility goal here, f prime x roughly equals fx. So what you are saying is that x here may be a backdoor input. Is that what you mean?
Yeah, I mean, when we formalize two goals, we all try to formalize the similarity of these features, right? Isn't that overlapped?
If here, for example, here, if x in this slide, okay, if x is really only includes image without the backdoor, and the backdoor, then the backdoor trigger, okay, the backdoor trigger is very unique, which does not really appear in any clean image, in any lecture images, then I think these two goals do not have overlaps. But if there are some lecture images which may include, unfortunately, the backdoor trigger, then they may have some overlaps. Yeah, especially for those particular images. Yeah, I hope that answers your question. Does that make sense?
Yes, thank you.
Okay.
All right, cool. So next one is Xinyu.
Hi, Professor Niu Gong. I'm Xinyu, and I have a question about the linear probing downstream tasks. So I'm wondering, how many epochs have you tried to train the downstream task? Because if the epoch increase, I thought the attack success rate might be affected, maybe by immediately.
That's a good question. That's a good question. So let me repeat the question first. So the question is, how many epochs did we use to train the downstream classifier, even if we use linear probing? And how does the number of training epochs impact the attack's success rate, right? That's a good question. Unfortunately, I don't remember whether we have explored this. Okay, maybe the details can be found in our paper. maybe we have explored the impact of the number of training epochs used to train the downstream classifier. But I think, but let me talk about another paper, poison encoder, which I won't talk about the details today, unfortunately. But in that paper, I clearly remember, because it's more recent, I clearly remember we did explore the number of training epochs for the downstream classifier, and it does have some influence on the attack's success rate. Okay, and because if you train for, if you're training, actually in that paper, what we found is if you train the downstream classifier using less number of epochs, the attack is less successful, but your classifier's accuracy is also smaller. So there is a trade-off between attack success rate and your classifier's accuracy. Yeah. So let me probably after the talk, I can check my paper whether we have evaluated this number of training epochs for bad encoder as well. Yeah.
Thanks.
Okay.
All right. So the last one for now, Ziyang.
Hello, I'm Ziyang Sha, a student from CISPA, and it's a nice talk. And I want to ask, what's the main difference between your bad encoder and Benjol's latent backdoor? Because latent backdoor is also in the transfer setting, and I want to ask what's the main difference, and that's it.
That's a very good question, Jiang. Thanks for the question. One difference is their latent backdoor is for a teacher model, which is still trained using supervised learning, right? So, so that's one difference, conceptual difference. Okay. Technically speaking, I think there are also technical differences in terms of how we embed the backdoor into the teacher model or into the encoder. I think their attack requires some labeled data from the target downstream task in order to attack. So let's say attacker wants to attack a certain target downstream task. Their attack needs a large amount of labeled data from that task in order to embed the backdoor into the teacher model. But as you can see, our attack does not have this requirement. Our attack requires attack data set, but the attack data set is unlabeled and does not need to be from the target downstream task. Yeah, but we also compared with their attack empirically in our paper. Yeah. You can also refer to more details in the paper. I hope that answers your question, Ziyang.
Yeah, it's good. But I think you, in your inject process, you use a reference image.
But just one, right?
Okay. So, but it's also from the downstream.
Yes, the reference image is from the downstream task, but it's only one.
Okay, thank you.
Okay, good question.
All right, so we have still one more question.
Okay.
Ning? Or you can directly ask, I think, yes.
Okay, thank you, Professor Nin. I have a small question. If I give you two model, that's the F and F prime, that's the clear model and adversary model, can you distinguish between them? Can you detect what is the adversary model, where the adversary model, and where the clear? Yeah.
Sure. Yuin, right? Did I pronounce your name correctly? Okay, that's a very good question. So you are basically talking about the defense, right? We have now I gave you an encoder. Can you detect whether it's backdoored or not? Okay, that's a very good question. So what I can tell you is that existing methods do not work. So so we have already seen multiple methods to detect backdoor classifier. Okay, so but they are designed to detect the backdoor classifiers. And when we generalize those methods to detect our backdoor encoder, they fail. That's what we know now. But I think this is definitely a very interesting future direction to explore, how to detect the backdoor encoder, and if it's backdoor, how can we recover the backdoor encoder to be a clean one? Yeah, I hope that answers your question. Yeah, it's a very good question.
Yeah, thank you.
All right, Neil, please continue, I guess. Yeah.
Okay, let's move on to part 2 about data auditing for pre-trained encoders. So recall that in self-supervised learning, a service provider such as OpenAI often collects unlabeled data from the public internet, uses them to pre-train encoders, and then may monetize the pre-trained encoders by deploying them as paid cloud services for the downstream customers. For instance, OpenAI monetizes its GPT models as a paid API service. The price of this API could be as high as $0.6 per 1,000 natural language tokens. So our public data are used to pre-train encoders and then monetized by service providers, even if we didn't authorize them to do so or get paid. So this motivates us to study data auditing for self-supervised learning. In particular, we aim to answer the following question. Was my public data used to pre-train a given encoder without my authorization? Such unauthorized data use already happens in the real world and leads to severe legal consequences. For instance, Twitter demanded an AI company stop collecting images from its website. A company called Ever uses its users' images to train face recognition models without the user's authorization. And FTC orders Ever to delete the trained face recognition models. We propose encoder MI, a membership inference-based data auditing method for pre-trained encoders. Given an encoder, which we call target encoder, and an unlabeled image, our encoder MI aims to infer whether this unlabeled image was used to pre-train the target encoder or not. If yes, we call the unlabeled image a member of the target encoder's pre-training dataset. Otherwise, we call it a non-member. In our method, we consider that the data auditor has a black box access to the target encoder. Specifically, given any image, we can query the target encoder to obtain its feature vector. Recall that self-supervised learning aims to pre-train an encoder such that it produces similar feature vectors for 2 random augmented views of an image. Suppose we are given a mirror image of the target encoder's pre-training dataset. We create 2 random augmented views using data augmentation. And we use a target encoder to produce a feature vector for each augmented view. Suppose we are also given a non-mirror image. We also create 2 random augmented views using data augmentation and use a target encoder to produce a feature vector for each of them. Our key observation is that the target encoder is likely to produce more similar feature vectors for 2 random augmented views of the mirror image, but less similar feature vectors for the 2 random augmented views of a non-mirror image. Based on this observation, we propose our encoder ML. Suppose we aim to infer the membership status of an image. We first create n random augmented views using data augmentation. Then we use a target encoder to produce a feature vector for each augmented view. Finally, we calculate the pairwise similarity scores between the n feature vectors. In our experiment, we use cosine similarity. Based on these pairwise similarity scores, we use a binary classifier, which we call inference classifier, to infer the membership status of the image. As you can see from this pipeline, the inference classifier is a key component of our encoder ML. And we build the inference classifier via shadow training. which we discuss next. In our shadow training, we assume the data auditor has access to some unlabeled images, which we call shadow data set. We evenly divide the shadow data set into two halves. One half is called shadow memory set, and the other half is called shadow long memory set. We first pre-train an encoder, which we call shadow encoder, using the shadow memory set. The shadow encoder may have a different architecture from the target encoder, and the self-supervised learning algorithm used to pre-train the shadow encoder may also be different from the one used to pre-train the target encoder. Based on the shadow encoder, we construct a training set for the inference classifier. Specifically, for each image in the shadow memory set, we create n random augmented views, and we use the shadow encoder to produce their feature vectors. And finally, we calculate the pairwise similarity scores between the n feature vectors. We treat these pairwise similarity scores as the features of the image. Since the image is in the shadow memory set, we assign a label 1 to it. For each image in the shadow long memory set, we also create n random augmented views using data augmentation, and then we use a shadow encoder to produce their feature vectors. And finally, we calculate the pairwise similarity scores between the n feature vectors. Again, we treat these pairwise similarity scores as the features of this image. And since this image is in the shadow long memory set, we assign label 0 to it. Our training set for the inference classifier basically consists of these features and the corresponding labels of the images in the shadow memory set and the shadow long memory set. Based on the training set, we build an inference classifier. In particular, we consider 3 ways to build an inference classifier. The first way is to rank the pairwise similarity scores of each image in the training set, and then train a vector-based classifier. The second way is to directly treat the pairwise similarity scores of an image as a set and train a set-based classifier. And the third way is to calculate the average of the pairwise similarity scores of each image and build a threshold-based classifier. Specifically, a threshold-based classifier infers an image as a member if its average pairwise similarity score is larger than a threshold. In our experiment, we pre-train a target encoder using MoCo, Cepha10 dataset, and Reslet 18 architecture. When pre-training a shadow encoder, we use SimCLR, STL10 dataset, and VGG11 architecture. As you can see, the pre-training algorithms, pre-training datasets, and the encoder architectures are different for the target encoder and the shadow encoder. The parameter n is set to be 10. We also evaluated our method in many other experimental settings, and the details can be found in our paper. To evaluate our method, we consider 10,000 ground truth members and 10,000 ground truth long members of the target encoder. We use accuracy as an evaluation metric, which is the fraction of the members and long members whose membership statuses are inferred correctly by our method. We also considered precision and recall as evaluation metrics, and the details can be found in our paper. This table shows the accuracy of our method when using different inference classifiers. As the table shows, our method is effective. We also evaluated our method on CNIP, a real-world encoder pre-trained by OpenAI. A key challenge of evaluation on CNIP is that how to collect ground truth members and long members of CNIP, since its pre-training dataset is not publicly disclosed. However, we know that CNIP uses public data on the internet, such as Flickr. So we collected images from Flickr to construct members and non-members of CNIP to evaluate our method. Specifically, we first collected 1,000 images from Flickr, and we treat these images as potential members of CNIP. We collected another 2,000 images from Flickr, randomly paired them to be 1,000 images. And then we treated these 1,000 images as ground truth non-members. Finally, we use our encoder MI to infer the membership statuses of these potential members and ground truth non-members. This table shows the accuracy of our method for CNIP when the inference classifiers are trained in our previous experiments. As we can see, our method is relatively accurate for CNIP. To summarize a little bit, I hope I have convinced you that data auditing is an emerging problem for pre-trained encoders in self-supervised learning. And the feature similarity between augmented views can be used to audit unauthorized data use in pre-trained encoders. Self-supervised learning also has many other security issues. For instance, we found that self-supervised learning is also vulnerable to data poisoning attacks. Specifically, an attacker can carefully craft some poisoning input and publish them on the internet. When a service provider collects unlabeled data from the public internet and uses them to pre-train an encoder, the encoder is poisoned. And the downstream classifiers built based on the poisoned encoder will predict attacker-chosen testing input as attacker-chosen labels. We also found that an attacker can steal a pre-trained encoder, which is deployed as a cloud service, while querying the encoder. The stolen encoder has similar utility with the target encoder, but stealing an encoder takes much less data and computation resource than pre-training an encoder from scratch. To conclude, in this talk, we mainly showed that pre-trained encoders in self-supervised learning are vulnerable to backdoor attack and how we can audit unauthorized data use in pre-training encoders. Finally, I'd like to acknowledge my students in this research. So that concludes my presentation. And let's see, do we have any more questions?
All right, so
thank you so much. I just wanted to thank Neil for this really great talk, and I need to leave now, but I will leave you in the capable hands of Yang, who's kindly volunteered to step in to sort of moderate the Q&A. I will stop the stream so that if people want to ask sort of off the record questions, they can do that. And thanks again, Neil. I hope to see you soon at some conference or something.
Yeah, sure.
Great.
Yeah, yeah. Thanks for the invitation again. Yeah.
Great. Thank you. Thank you so much.
Yeah.
All right, guys. So I'm the temporary moderator for the Q&A, and are there any questions?